Hi everyone, welcome to video number 7 of Physics Mechanics. In this video, you're going to learn several interesting topics, such as determining the bounciness of objects and simulating collisions. When two objects collide, it seems like their velocities change instantly from one number to another. However, we already know that acceleration is what causes velocity to change, and it doesn't change velocity instantly from one number to another, but rather continuously changes the velocity of an object over a period of time. So how do collisions work? Let's dive right into it. Let's take a look at what happens to a soccer ball when it bounces. You can see that when the ball is in contact with the ground, it becomes compressed for a moment and then returns to its original shape. This is how collisions work. To prevent one object from sinking into another, both objects are temporarily compressed until they are no longer in contact. The wooden floor is also being compressed, but since it's much harder than the soccer ball, you can't see it. During a collision, a force is applied while the objects are in contact. You will later see that this is an example of impulse. But before we get into impulse, let's talk about what determines the bounciness of balls. The factor that controls bounciness is elasticity, or the ability of an object to return to its original shape after it's distorted. We can see why elastic objects are bouncy. When the object returns to its original shape, it pushes down on the ground, so the ground exerts an upward force on the object, allowing it to bounce upwards. There are several factors that determine the elasticity. The material itself is one factor. Rubber is an elastic material because internal tension causes it to return to its original shape. Another factor is the inside of the ball. If the inside is air, the ball is more elastic, assuming the air is maintained to a certain pressure. This is because when the ball is compressed, the air pressure forces the ball to return to its original shape. However, flat balls don't bounce much because the air pressure isn't enough to force the ball to return to its original shape. Squash balls are an interesting example of air pressure. They don't bounce much by themselves. However, if they get warm, the air pressure increases, allowing the ball to bounce higher. Some objects aren't bouncy. These objects usually are made of inelastic material and/or aren't filled with air, but rather solids that rub against each other. The solids that rub against each other cause a lot of friction, which turns the kinetic energy used to make the object bounce into heat energy. You will learn more about energy in the next video. The elasticity of the ground is also an important factor. Hard surfaces are elastic because they hardly change their shape. Soft surfaces, such as carpet, may not be elastic because they don't return to their original shape. Inelastic surfaces absorb kinetic energy from a bouncing object and turn it into heat energy, which is why they aren't as bouncy as elastic surfaces. Now that you know what determines the bounciness of objects, let's dive deeper into collisions. We will first learn about momentum, which, if we're given enough information, can be used to determine the velocities of objects after a collision. Then we will learn about impulse, which can be used to determine the force on objects while they're in contact, or the amount of time that they're in contact. Formula for momentum is very simple. It's mass times velocity. And the units are kg, which is mass, times meters per second, which is velocity. And we're first going to deal with 1D momentum. And remember that you have to designate a direction to be positive. And if an object is traveling in the opposite direction, then the velocity is negative. So that means that the momentum is also negative. So momentum is useful because of the law of conservation of momentum, which states that the total momentum of a system is conserved as long as there is no outside force. So let's suppose that we have a system in which a 10 kilogram block is traveling rightwards at a velocity of 9 meters per second towards a 5 kilogram block at rest. And we're going to ignore friction and other outside forces. So the momentum of the 10 kilogram block is 10 times 9, which is 90. The momentum of the 5 kilogram block is 5 times 0, which is 0. So the total momentum is 90. Afterward, let's suppose that the two blocks stick together once they collide. This is called an inelastic collision. In this case, the momentum is equal to the total mass of the blocks, which is 15, times the velocity, which we're going to denote as x. And it's equal to the total momentum before, which is 90. And now you can solve for x to get that it is 6. So the two blocks travel rightward at a velocity of 6 meters per second after they collide. Now we're getting into 2D conservation of momentum. So in this case, you have to consider both the x and y velocity and momentum of each object, and both the x and y momentum will be the same before and after. So let's suppose that we have a system in which two blocks are in space, and a 10 kilogram block is moving rightward at a velocity of 2 meters per second and downward at a velocity of 1 meter per second. And a 5 kilogram block is moving rightward at a velocity of 0.5 meters per second and upward at a velocity of 2 meters per second. The momentum, the x momentum of the 10 kilogram block is 10 times 2, which is 20. The y momentum, well, in this case, we have a block going upward and a block going downward. So we have to designate one of the directions as positive and one as negative. Usually upward is positive, so downward is negative. So the y velocity is -1, which means that the y momentum is 10 times -1, which is -10. Similarly, you can compute that the x momentum of the 5 kilogram block is 2.5 and the y momentum is 10. So the total x momentum is 20 plus 2.5, which is 22.5, and the total y momentum is -10 plus 10, which is 0. We're once again going to assume an inelastic collision. So the total x momentum is the total mass, which is 15, times the x velocity, and it's equal to the total x momentum before, which is 22.5. And for the y velocity, we don't know if it's going to be upward or downward because there was one block going upward and one block going downward originally. But since positive is upward, we're going to draw the vector for the y velocity upward for now, and if necessary, we will adjust it. So the total x momentum is 15 times x, which is 22.5. The total y momentum is 15 times y, which is 0. And you can solve to get that x is 1.5 and y is 0. So now you can just get rid of the y velocity vector. Here's a practice problem. If you want to give it a try, pause the video here. The solution will come in 3, 2, 1. So suppose that right is positive and left is negative. We first need to compute the total momentum before the collision. That is equal to 10 times 100 plus 50 times -10, which is 500. And after the collision, the total momentum is still 500, and it's equal to 10 times the velocity of the 10-gram block plus 50 times 5. And you can solve to get that v is equal to 25. So the speed is 25 meters per second, and since v is positive, the block is traveling right. Here is another practice problem. For this one, you're going to have to use content that you learned back in video number 2. If you forgot, then just watch the first part of the solution. But if you want to give this problem a try without watching the first part of the solution, pause the video here. The first part of the solution will come in 3, 2, 1. So before, you just have a 10 kilogram block moving rightward at a velocity of 60 meters per second. And after, you have a 7 kilogram block and a 3 kilogram block. The 7 kilogram block is moving at a velocity of 42.42 meters per second, 45 degrees north of east. You have to break this down into its components. To do that, for the x component, you just multiply the magnitude by cosine of the angle north of east. For the y component, you multiply the magnitude by sine of the angle north of east. And in both cases, you're going to get that the velocity is 30 meters per second. Pause now if you want. The rest of the solution will come in 3, 2, 1. So now you have to find the total x momentum and the y momentum before the explosion. So the total x momentum is 10 times 60, which is 600. And the total y momentum is 10 times 0, which is 0. And 600 is equal to 7 times 30 plus 3 times Vx, where Vx is the x velocity of the 3-gram block. You can solve to get that Vx is 130 meters per second. And similarly, 0 is equal to 7 times 30 plus 3 times Vy, where Vy is the y velocity of the 3-kilogram block. And you can solve to get that it is negative 70 meters per second. The problem asks for the speed and direction. The speed, you just use the Pythagorean theorem to get that it's 147.65 meters per second. And the direction is arctangent of negative 70 over 130, which is negative 28.30 degrees north of east. And you usually don't want a negative, so this is just 28.30 degrees south of east. Now we're getting into impulse, which is a force applied over a period of time. The variable for impulse is delta p, and you'll see why soon. The formula is delta p equals F times delta t. We're going to derive a very important theorem called the impulse momentum theorem. We're going to start off with A times delta t equals delta v. This comes from one of the 5 kinematic equations. Multiply both sides by m, and you know that ma is equal to F, so you can just substitute that in to get that F times delta t equals m times delta v. And you know that F times delta t is the impulse. So what this theorem tells us is the impulse is also the change in momentum. And this is why the variable for impulse was delta p. This is a very useful theorem that can be used to explain numerous phenomena. For example, why does it hurt more if you fall on a concrete floor rather than a trampoline? The first thing you need to realize is that F and delta t are inversely proportional, so when one increases, the other decreases. A trampoline is very soft, so when you fall on it, it will go down with you, and there's going to be quite some bit of time that elapses while you're in contact with the trampoline before the trampoline returns to its original shape. So delta t is relatively high, and that means that the force is relatively low. So that's why it doesn't hurt so much. But if you fall on a concrete floor is very hard, so it's not going to be applying the force for as much time. And since it also has to bring you to rest so you don't sink into the floor, that means that the force has to be higher. And that's why it hurts more if you fall on a concrete floor. So here's a practice problem. If you want to give it a try, pause the video here. The solution will come in 3, 2, 1. So you just use the impulse momentum theorem, and you plug in the values you know. You know the force is 2, the mass is 0.1, and since the ball did not bounce up, that means that its final velocity is 0, so the change in velocity is 5. And you can get that delta t is equal to 0.25 seconds. Here's another practice problem. If you want to give it a try, pause the video here. The solution will come in 3, 2, 1. For part A, you use the 5th kinematic equation to find the velocity of the object when it reaches the floor. So Vf, which is the velocity when it reaches the floor, squared equals 0 because there's no initial velocity, squared plus 2 times the acceleration times the distance. And solving for Vf, you'll get that it is 14 meters per second. So when the object bounces upward, it will have an upward velocity of 50% of 14, which is 7. And the velocity was originally 14 meters per second downward when the object reached the floor. And you have to keep the direction consistent. So this is negative 14 meters per second upward. And you can find that the change in velocity is 7 minus negative 14, or 21 meters per second. So the impulse is 5 times 21, which is 105 kilograms times meters per second. For part B, you use the fifth kinematic equation to solve for the height of the object when it reaches its peak. The final velocity is 0 because that's when the object is at its peak. So 0 squared is equal to 7, which is the initial velocity of the object after bouncing upwards, squared plus 2 times the acceleration of negative 9.8. Keep in mind you need that negative because the initial velocity was 7 upwards and acceleration x downwards times the height. And you can solve that the height is 2.5 meters. And 2.5 is not 50% of 10, so the object does not bounce to 50% of its original height. Your intuition might have said that it does bounce to 50% of its original height. That's what my intuition said. But after I performed these calculations, I realized that wasn't true. So it's important that you always do all necessary calculations in physics rather than just assuming. Here is a challenge problem. Since it's a challenge problem, it's fine if you don't get it right. But nonetheless, read over the problem because it's a pretty good problem and give it a try if you want. Even if you don't want to do it, still look over the solution because the solution is simple and elegant. But anyway, if you want to give it a try, pause the video here. The solution will come in 3, 2, 1. So we have to think back to video number 2, where we learned about projectile motion. First, we need to determine the amount of time the projectiles are in the air. This is always the same because the projectiles have no initial vertical velocity since the cannon is horizontal. Now suppose that t is the amount of time the projectiles are in the air, t is a fixed number, and v is the horizontal velocity of the projectiles when they leave the cannon. We have that the x displacement, or distance, in this case they're the same, is equal to v times t. So now we use the fifth kinematic equation to determine the relation between v, the velocity of the projectiles when they leave the cannon, and d, the distance the projectiles travel in the cannon. The final velocity is when the projectiles leave the cannon, so v squared equals 0 squared plus 2ad. Taking the square root, we get that v is equal to the square root of 2ad. And we know that the x distance is equal to v times t. And now we can plug in the value we determined for v to get that the x displacement is equal to t times the square root of 2ad. Now, using properties of square roots, we're going to move the square root of d outside. And now notice that t and a are both fixed variables. So t times the square root of 2a is just a constant. And that constant is c. So we get that the x displacement is equal to c times the square root of d. So therefore the answer is B. I hope this video was really interesting and helpful. In the next video, we will learn about energy, which is something you hear all the time and a very useful concept in physics and other fields too. Knowing energy will also allow you to solve even more collision problems. Momentum can only help you solve collision problems if you're given the velocity of one object after the collision or know that the collision is inelastic. With energy, you can solve collision problems without knowing either of those. Thanks for watching. I'll see you in video number 8.